Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to our Organic Chemistry 1 class. Today we will start on Chapter 11, Ethers, Sulfides and Epoxides. And as usual we will cover nomenclature, structure and properties, preparations and reactions. Nomenclature of ethers. First, a systematic IUPAC name which constructed by choosing the larger group to be the parent alkane and naming smaller group as alkoxy substituent. For example, here 1, 2, 3, that's a long chain, so it's propane. On carbon 2 we have methyl and we have methoxy. So it is 2-methoxy, 2-methyl propane. In this compound, the long chain containing double bonds, so this is a parent, so it is 6 carbon, so it's hex. 1 will be this carbon, so it's 1 in, 1, 2, 3. On number 4 we have ethoxy, so it is 4 ethoxy, 2 methyl, 1 in. In this compound, that's carbon, that's 2 carbons, and here is methoxy and here is methoxy, so this is 1,2-dimethoxyethane, that's glyme, common name. This is a cyclic ether tetrahydrofurane, IUPAC name oxolan, 1,4-dioxane, 6-member ring containing 2 oxygen. Second, a common name is constructed by identifying each R group, arranging them in alphabetic order, then adding the word ether. Here we have methyl group and here we have tertiary butyl group around the oxygen. So this is tertiary butyl alphabet, methyl, ether. In here we have ethyl group and we have ethyl group, so this will be diethyl ether. Provide a IUPAC name for each of the following compound. Here we have chiral center, it's S configuration. Here is 1, 2, 3, and here is ethoxy group, so this is 2-chloro, 1-ethoxypropane. For this compound, we have cyclohexene, and on carbon number 1, we have ethoxy, so it's 1-ethoxy, cyclohex 1-ene. Physical properties of ethers. An ether molecule has a net dipole moment due to the polarity of the CO bond. Okay. The boiling point of ether is comparable to the alkanes but much lower than that of alcohol of comparable molecular mass, despite the polarity of the CO bond, because alcohol has hydrogen bond, ether does not. Ether molecules are miscible with water because ether is proton acceptor. This is contribute to the fact that, like alcohol, oxygen atom of ether can also form hydrogen bond acceptor with water molecule. Ether, ethers can interact with metal coordinate bond that have either a full positive charge or a partial positive charge. For example, Grignard reagents are formed in the presence of ether, which supplies the Grignard reagent by coordination. Cyclic polyethers containing multiple oxygen atoms are capable of binding more tightly to metal. The unique properties of these compounds derive from the size of their internal cavities. For example, internal cavities of 18, and we will come to know what's that, crown 6, comfortably host the potassium cation. In this way, 18 crown 6 is capable of solvating potassium ions in organic solvents. Normally, the metal cation by itself would not be soluble in nonpolar solvent. The crown ether named X crown Y, where X indicates the total number of atoms in the ring. Y represents the number of oxygen atoms. So here we have how many atoms? A total of 12 atoms. How many oxygen? We have 4. So we say 4 crown 4, 12 total. Crown because of that shape. And 4 is the total number of oxygen. Here we have 15. How many oxygen? 5. So it's 15 crown 5. That's what we were talking about here. That's 18 crown 6. See, the first one solvates well lithium. 15 crown 5 solvates sodium, while 18 crown 6 solvates potassium very well. This field of host-guest chemistry led Charles Pedersen, who discovered the crown ethers, and Donald Graham and Jim Mary Lynn to share Nobel Prize of 1987. Identify the missing reagent needed to achieve the following transformation. For this one, we have here potassium fluoride, and we would like to get the fluoride ion free. So we have to catch up the potassium. To solvate the potassium, we need 18 crown 6. We have here sodium fluoride. We would like to solvate the sodium, so we use 15 crown 5. What about lithium fluoride? If we use lithium fluoride, then we need 12 crown 4. Preparation of ethers. We can prepare ethers by dehydration of alcohols. For example, diethyl ether is prepared industrially via acid-catalyzed dehydration of ethanol. The first step is protonation in acid medium, so forming the oxonium ion. Then another molecule of ethanol will attack as a nucleophile, ejecting the water molecule out via SN2 mechanism to form the oxonium salt, which deprotonate to give the ether. Another synthesis called Williamson ether synthesis, taking the alcohol treated with very strong base like sodium hydride to form the alkoxide. the alkoxide acts as a good nucleophile to attack on another alkyl halide molecule to give ethers. But we have to be very careful that alkoxide can act as a base as well. So, why is the following reaction a poor method for synthesis of tertiary butyl propyl ether? What would be the major product from this reaction? Propose a better synthesis of tertiary butyl propyl ether, having propyl alkoxide, sodium propoxide, with tertiary butyl bromide to give the desired product. Why this is not right method? As we mentioned that alkoxide can act as a nucleophile as well as a base. So the desired SN2 cannot occur in this case because this is a tertiary alkyl halide. A tertiary alkyl halide prefer the E2 mechanism elimination reaction, and what will be the product is alkoxide act as a base, taking the hydrogen out, forming a double bond, kicking the Br out to form isobutene. The better synthesis would be switching using bulky alkoxide but unhindered alkyl halide. So we start with the primary propyl bromide and sodium tertiary butoxide, then we'll have SN2 reaction and the desired product can be formed. Alkoxymercuration-Demercuration method. Please go and see lecture 32. It's alkene plus mercuric acetate in presence of alcohol to give this intermediate, which upon treatment with sodium borohydride, it gives the ether addition of HOR in Markovnikov orientation. So starting with but1-ene, here this carbon carries only one hydrogen, this carries two hydrogen. So after mercuration, adding mercuric acetate in methanol, then reduction with sodium borohydride, what will happen that the hydrogen will add to carbon carrying more hydrogen here. So the hydrogen will add here, and the methoxy will add on this carbon to form 2-methoxybutane. Regarding the mechanism, as we mentioned before in lecture 32, acetate will be forming the acetate ion and mercury plus species, which add to the double bond to form the bridge mercurinium ion, which in resonance with this carbocation and that carbocation, the alcohol will add to the carbon carries more substituent to form the oxonium, which deprotonated to form the OR. Upon reduction with sodium borohydride, it gives the ether. Reactions of ethers. Acidic cleavage. Ether reacts with excess hydrogen halide and heat gives mixture of alkyl halides, R halide, R halide. Both hydrogen iodide, hydrogen bromide can use to cleave ethers, while HCl is less effective. But hydrogen fluoride does not cause acidic cleavage of ethers. This reactivity is a result of relative nucleophilicity of the halide ions. So ethers oxygen protonate as a first step, proton transfer, to form oxonium. Then halide will act as a nucleophile and kick alcohol molecules out, ROH, to form alcohol and methyl halide. Then alcohol gets protonated again, form oxonium, followed by nucleophilic attack, displacement reaction, and to give another species of alkyl halide. Certain ethers, those containing tertiary alkyl or benzyl or allyl group, cleave via SN1, not SN2, as a previous slide. So, tertiary butyl methyl ether protonate in the first step, form oxonium ion, cleave, dissociate to form carbocation and alcohol. The carbocation, either via SN1, will lead to the formation of alkyl halide, or via E1, where X- would act as a base and to form alkene. When phenyl ether is cleaved under acidic conditions, the products are phenol and alkyl halide. The phenol is not further converted to alkyl halide because neither SN2 or SN1 process are efficient in sp2 hybridized center. So we get this protonated first, then X- will attack on R, cleave to form phenol. Phenol is not further protonated, and then SN2 reaction or SN1 reaction takes place. This is not the case. It may be protonated, but at equilibrium with protonated, deprotonated species, but still just only phenol. Autooxidation of ethers. Ethers undergo autooxidation in the presence of atmospheric oxygen to form hydroperoxide and dialkyl peroxide. The general equation ROCH2R prime, the displacement of one of these hydrogens by OOH, or oxygen by OO bond, so it will form hydroperoxide and dialkyl peroxide. Here is diethyl ether in the presence of oxygen will form 1-ethoxy, 1-hydroperoxyethane, and ethyl peroxyethane, what we call it diethyl peroxide. So this hydrogen, one of these hydrogens, will be replaced by OOH, or one more oxygen will be inserted between here and form the peroxide. And peroxides are well known to be explosives. That's why we have to be sure that our ether we use in the lab is peroxide free. Usually we buy ether sealed under neutral atmosphere like nitrogen or argon. And once you open, try to use the ethers. Don't keep it in the lab for long. Mechanism. Any initiator in the media will take one of these hydrogen out, forming this radical as the initiation step. At the propagation step, this radical will react with oxygen molecule to form peroxy radical. Peroxy radical again will have that hydrogen from another molecule of ether to form the hydroperoxide. To terminate any radical with any radical coupled together to form neutral species will terminate the reaction. Epoxides. Epoxides means three-membered ring with oxygen. That's highly popular at our level. We have here also another type of oxygen containing ring, 4-member ring, 5-member ring, and 6-membered ring. But the epoxides at that level we will cover. Nomenclature. Hantzsch-Widman nomenclature. This systematic nomenclature applies to monocyclic 3 to 10-membered ring heterocycles. The type of heteroatom is indicated by prefix as shown below. For oxygen we give it oxa. For nitrogen we call it aza. For S we call it thia. For phosphorus we call it phospha. The ring size indicated by the suffix. So we can get for 3-member ring ir, 4-member ring et, for 5-member ring O. So for the 3-member ring, oxa for oxygen, then Eren, that's for the saturated ring, okay? So this ring will be, because we can get two vowels A and I, so this eliminates, so it will be oxyrane. Again, here we eliminate, so it will be excitane. Oxetane. Here, oxylane for the 5-member ring. Okay, this is a systematic nomenclature for the oxygen-containing compound. Okay, we are talking in this chapter about oxyrane, epoxides. For the epoxides, we have two methods. The first one, the parent is considered to be the oxyrane, and any group connected to the epoxide are listed as a substituent. So here we have 1, 2, 3, because E comes first, methyl M comes second, so it's 2-ethyl-3-oxyrane. Here, the substituent, we have two substituents in this carbon. On that carbon, we have only one. So we'll consider the number 1, 2, 3. So it will be 3-methyl, 3-ethyl, 2,2-dimethyl oxyrane. The second way of naming this, the oxygen atom is considered to be the substituent on the parent chain, and the exact location of the epoxide moiety is identified with two numbers followed by term epoxy. The long chain here is this one. So this is pentane. On carbon 2 we have here methyl. So it's 2-methyl. Then on carbon 2 and 3 we have the oxygen of the epoxide. We call it 2,3-epoxy pentane. So the name is 2-methyl 2,3-epoxy pentane. By this, the same compound is 3-ethyl 2,2-dimethyl oxyrane. How to prepare epoxides? We have covered that in lecture 35. By peroxy acid oxidation of alkene. So if we have double bond with peroxy acid, we get a mixture of enantiomers. This one is 2s3r 2-ethyl 3-methyl oxyrane, and this one will be 2r 3s 2-ethyl 3-methyl oxyrane. That's a racemic mixture. Stereospecific reaction. So if we have cis, we get the meso epoxide, and when we have trans, we got enantiomers. In detail, this was covered in lecture 35. Preparation from halohydrin. Again, we covered this topic of the synthesis of halohydrin in detail in lecture 33. Alkenes can be converted into halohydrin when treated with halogen in the presence of water. So the first will react with bromonium ion to form bromonium bridge. Then the water will come and attack on the more substituted side and end up with alcohol and Br, OH and Br. We call it halohydrin. Halohydrin. Now, if the halohydrin now subjected to base, it forms the epoxide. Halohydrin can be converted into epoxide upon treatment with a strong base. The first step, OH base will take the hydrogen H out, leaving O minus, will attack as a nucleophile from the back side, ejecting the Br out to form epoxide. We have mentioned that again in E2 mechanism, that the substituent, the alkyl leaving group, and the attacking should be coming from the back side. Okay? So if you have this molecule and asked you, show what reagent would you use to prepare this epoxide, you will say, well, take this out, and that will be alkene with peroxy acid. Or have the OH up and Br down. If you have that chlorohydrin with base, will form this compound. How we can get this chlorohydrin? We get that from, again, alkene. Take this out and put double bond. That's it. Ring opening reactions of epoxides. Reactions of epoxide with strong nucleophile. The strong nucleophile will ring open the ring. So nucleophile like sodium cyanide, the cyanide ion, hydride ion here act as a nucleophile. are minus or partially negative charged organo alkyl magnesium halide, sodium sulfide. The sulfide ion here act as a nucleophile, or alkoxy will work as a nucleophile with ring opening. This reaction exhibits two important features that must be considered: regioselectivity and stereochemistry. Regiochemistry, when the starting epoxide is unsymmetric, the nucleophile attacks the less substituted, which of course will be less hindered position. So we have here the epoxide carbons. This one is substituted, has substituent, two substituent. This one is free, so the nucleophile will attack the less hindered and ring open. Stereochemistry, of course, if the epoxide ring up, the nucleophile will attack from the back, so the OH will be up, and the nucleophile like SH minus will be down. So starting with 1R2 S 1-ethyl 1,2-epoxy cyclopentane will give you 1R2R 1-SL2 mercaptocyclopentane 1-ol. Predict the product of the following reaction and draw likely mechanism for the formation. Treat this compound, this epoxide, with sodium cyanide. Of course, this carbon is less substituted and less sterically hindered, so the cyanide will attack on this carbon, taking this carbon oxygen bond, forming O minus, act as a base, take hydrogen, abstract hydrogen from water molecule to form the alcohol. OH is up, CN will be down. So this is a product. In case of acid-catalyzed opening epoxides, first step is proton transfer, forming oxonium. Again, the hydrogen, the oxygen from water will come and attack on the carbon carrying more substituent, okay? And again, the diol will be anti-orientation. OH is up, OH is down. So the first step, proton transfer, forming the oxonium, water attack as a nucleophile, opening, then deprotonation of this oxonium with another molecule of water to form the diol. Why the water molecule will come and attack on the more substituted carbon? Because again, the oxonium ion in resonance with this carbon have partially positive and this carbon carrying partially positive. This is a secondary, okay, secondary carbocation, and it's more stable than the primary carbocation, so the contribution of this will have more contribution than this one, so the water molecule will come and attack on this carbon. Predict the product of the reaction below and draw the likely mechanism of its formation. Okay, here is monosubstituted, this is disubstituted, react that with ethanol in catalytic amount of sulfuric acid, so this oxygen will gets protonated. Well, that's the oxonium. Then this will attack on the more substituted carbon, forming and ring opening, So this OH will be up, this this OR or ethyl will be down, protonated, then deprotonation with another molecule of alcohol to form ethyl OH in this configuration. Looking forward to seeing you in class. Bye bye.